So here's number 45. This one comes up almost every year, generally this stage in the game. So I've kind of skipped ahead. I've composed it where I've plugged x squared in for x already. And finding the domain, that's the part that usually is kind of confusing sometimes. So let's stick to what we know to be true and kind of see what unfolds as we go through here. So x squared plus 4 must be bigger than 0 because it's under the radical. Actually, I take it back. It could be equal to also, but it's under the radical. We can't take the square root of a negative number and get a real number out, and that's really the key here. For domain and range, we're still dealing with real numbers only, so that's the deal. We can't put a negative number under here and get a real number out. So in order to get a domain in our real number system, we're going to need to have this be bigger than 0 or equal to it. So let's run through and see how it's going to kind of shake out. X squared would be bigger than or equal to negative 4. And now if we take a square root, kind of hitting a few issues here. We're going to have, mainly it's the fact that we're going to get a complex number. I think I can leave it at that. Usually we would apply an interval test, but we don't have a real number, so it's going to be hard to do a number line in the real number system and do an interval test. But I think this is going to be where it's really kind of breaking down. Think of it this way. For domain, this is the way I always think about domain. Assume it's all real numbers unless there's somewhere you know it won't exist. All right, well, with the square root, we know that this stuff has to be bigger than 0 or equal to 0 or it won't exist. And if we keep going, this will tell us the places where we'll have a problem with our x values. The thing here is the place we're going to have a problem with our x values is a complex number. Two complex numbers, 2 and negative 2i. So there's no real place here that we're going to have an issue. That's kind of a good way to think about why it's all real numbers for your domain. There's no real place that's going to cause a breakdown here. So another way to think about it is kind of think about this piece right here. So just to pull up an old example, we did something like this, x squared minus 4, found the domain of that recently. Well, in that case, you ended up doing a number line and doing an interval test, and you check in the middle, put in 0, all right? Well, 0 squared minus 4 is not going to work out. This could be a complex number. But if I put something like 5 in here, all right, 5 squared is 25, I can subtract 4 and get a real number. And put something bigger than negative 2 like negative 5, same thing. So the interval test worked really well there. Got a little bit different situation here. You've got x squared that's always going to be positive. So let me make a little note of that. X squared is always positive. And then you're going to add 4 to it. So you can basically guarantee that whatever's under this radical is always going to be positive. That's probably, it's a little more, it's not really a proof-based way to look at it because it's kind of just thinking your way through it. But I think it is a logical way to look at this and hopefully make it make sense that it is just all real numbers. So 47 usually comes up as a question as I go over this assignment, because there's something going on here that's maybe a little different. I don't think we definitely haven't specifically talked about it yet. So here's my two functions, and I'm supposed to find f of g of x. So let's just kind of jump in, do it, and then talk about why what you probably ended up with may not have matched what the book said the answer should be. So f of g of x, it's pretty straightforward when we just plug square root of x in for x squared. So square root of x squared plus 1, and hopefully this is pretty straightforward. You square your square root, you just get x out. So that is the function, and all real numbers is definitely going to be the domain for that function. That's a line. It's x plus 1, so it's a line that goes on forever, both directions. Now your book says that's not necessarily a domain. It says it's everything greater than or equal to 0. So let's talk about why that's actually the case. And the trick here really comes down to the input function. Because g is getting put into f, this entire function here is a input on its own. So we need to take a look at which x values actually get passed on to the f function. So make sure that makes sense. We need to take a look at the domain of this function, because any x values that are not in this domain, they can't get passed on to f, so they won't show up in f. So we got to keep that part in mind. So let's find the domain of g of x. So there's not going to be a lot of work to do. X is under a radical, so it has to be positive or at least 0. So when we take a square root, we get a real number out. And that's the key here. We're working in real numbers. The graph is the graph we use is xy coordinate plane with real numbers. We have not got into the 4-dimensional complex graph yet. Eventually I'll talk to you about that. We're not there yet. So we're still in real numbers, and if we put a negative in here for x, it's not going to leave us in real numbers. We're going to leave that real system, so we're not going there yet. So your domain, x, is anything bigger than or equal to 0. So that means if I chose, say, -2 for x and plugged it in here, I don't get a real number out. So that means there's no real number to pass on to the next piece. And maybe just sort of another way to think about that before I put that final domain up there. Let's just write it the way you may have seen some of these before. Actually, I know you saw some of these because they were in the first part of the chapter. So let's suppose we have f of g of -2. Well, first of all, I put in -2 for x, and at this point, I've got sort of a, I don't know, it's not a real number. So there's no input to go any further. That's really where this is breaking down. So in the end, the final domain, even though for x plus 1 all real numbers do work, only 0 and positive numbers are actually being passed on to that function. So that domain restriction carries through. So the actual domain here is x is greater than or equal to 0. I picked 77, sort of at random. This little section, I usually have one question. Usually students say, can you just do one of these? So this one's a pretty good one. There's no definite, like this is definitely the way to do it, but there's kind of a, this is probably how you want to handle it. This is going to lead into something called the chain rule. I think I mentioned that earlier. That's going to be one of your big rules in calculus you're going to end up using. So that's why we're developing this skill now. So if you're kind of used to doing this process, when you cover that chain rule, you already know what to do, and then you can focus on just doing the calculus part. So what you really want to think of is sort of like factoring. What do these things have in common? And hopefully you're noticing right away, well, they got an x plus 4 in common. So instead of just factoring that out, let's think about defining that as a function. So this is really, you can call it f, g, a, b, whatever you want to call it, whatever function you want to call it. I'm just going to call it g of x. So I'm going to call g of x x plus 4. Okay. So now think about how this might get composed, how we could maybe write a function f, another function, where when this gets plugged in, here's our results. It's sort of going backwards from what you've done for the rest of the lesson. And if this came out, and since it's f of x, this is going to be replaced with an x. And so will this part. So that's really all there is to it. Hopefully that kind of clears it up. Because now if I did f of x, I'm sorry, f of g of x, this plugs into f of x, and now that's the function we'll end up with.
Before we do 82, I thought I'd share this Ripple tank with you. It's really good for all sorts of wave applications like sonic booms and double slit experiment. We'll mess around with some of this stuff when we get through trig. I added it to the website. If you look at the chapter 1 notes, if you want to play around with this, it's down there. But 82 talks about dropping a rock in a pond and kind of talking about what happens with that. So you probably have done it before and you kind of know the idea, but this is sort of what we're looking at. We're looking at how big are these circles as time goes on. That's kind of the gist of the problem. So let me dive into math and I'll explain more about that.
Now for the actual math of 82. So 2 parts going on, but really we just want to have the ripples, or how big the circles are based on how much time has gone by without having to do 2 problems in one. So it's sort of like making your life easier by taking 2 math problems and combining them to 1 math problem. So first of all, we know that the radius of each little circle going out through the water is going to change as time goes on. And from geometry, we know the area of a circle, and we know that's defined by the radius as the input. The bigger the radius, the bigger the area is as an output. So if we put the two things together, now I can tell how big the circle is going to be using a stopwatch. So it takes a little bit of the measurement out of it, I guess. Makes it a one-step problem instead of a two-step problem. So that's the idea. And really, there's not a ton of math going on here. We're going to take the 0.6t and plug it in to the r over here. So in the end, it would be pi times 0.6t squared. Okay. If you square 0.6, you get 0.36 times the pi, and then t squared. I kind of changed the order, but that usually looks a little nicer. Typically, we put constant first, pi next, variables after pi. That's kind of the typical format. Commutative property says we can switch any of these. Let me kind of put in parentheses. There's three terms here. We can switch those in any order since they're being multiplied and still right. So if you had a different order, that's fine. But those are the three pieces you should have.